I may have misspoken in the last lesson. We were talking about cubic splines, and I had mentioned that piecewise quadratic splines would fit the data better than piecewise linear. Further investigation into that matter has led me to think otherwise, as we will soon find out. Notice that a piecewise linear interpolation hits the specified data points exactly. However, it lacks continuity of slope. That is, the slope is different on the left side of a given data point than on the right side. There is an abrupt kink, so to speak. Upgrading to quadratic splines would allow us to impose another constraint, namely the continuity of slope. I had thought that would give us a smoother, better fit to the data. This is what I discovered. Yes, the fit is smoother, but I'd argue that it is not better. Notice that it oscillates between the data points. This is the very reason we chose cubic splines in the first place, because they're supposed to eliminate the oscillation of Runge's phenomenon. It doesn't look like quadratic splines help us out in that department. To get a little more technical, I actually discovered that we had an under-constrained system of equations. This means there are an infinite number of possible solutions to interpolate data using quadratic splines. Here is shown a second possible solution. This is a third possible solution. Notice it is slanting more to the left each time. Meanwhile, the splines still pass exactly through the orange data points, and the slope is the same on the left and right side of each data point. Another possible solution, even more slanted. Interestingly, the right tail oscillates much less as the left tail increases in oscillation, at least for the time being. Yet another possible solution. At any rate, none of these appear to fit the data as well as we'd like. And again, remember that there are an infinite number of possible solutions. I'm sure you get the idea by now. I could keep going, but I'll stop with this image of yet another possible solution to interpolate the orange data points with quadratic splines. If you missed the earlier lessons on interpolation with cubic splines, I'd recommend viewing them before we proceed. The following derivation echoes what we already covered in those lessons. So we start by splitting our data into 6 equally spaced segments. This time, each function is second order instead of third order. The coefficients a, b, and c are unknown as of now, but we will solve for them using a few tricks. As with cubic splines, we impose continuity of position, seen color-coded at top. What this means is that the right endpoint of each segment must meet the left endpoint of its neighbor, and vice versa. That way, we don't have any jumps or gaps in our interpolating curve. Continuity of slope is seen in the bottom 2 lines. This means that the slope to the left of any given data point is equal to the slope on the right. That makes the curve smooth without any kinks at the joints between neighbors, as we saw with linear segments. Given any second-order polynomial, the derivative can be found by employing the power rule of differentiation term by term. That is shown in the second line. Below that, we evaluate the function and its derivative at the left and right endpoint. Remember that t ranges from 0 to 1 for each segment, so the left endpoint corresponds to t equals 0, and the right endpoint to t equals 1. Y sub I is a data point, which is known. D sub I is a slope, or derivative, at that point, which is unknown. From the previous equations, we solve for a, b, and c in terms of y and d. Now we impose continuity of slope, make some substitutions, and clean up the expression to look like it does in the last line. This was done for the point between f0 and f1, but a similar process can be done for every other data point. The result of that is seen here. Remember that all the y's are known. They come from our data table. The d's are all unknown. So we have 7 unknowns, but only 6 equations. That's what I meant earlier when I said the system of equations was under-constrained. That's why there are an infinite number of solutions. To home in on a single solution, I need to introduce a new equation. So I decided to impose the constraint of symmetry. This is done by making the slope at the leftmost endpoint equal to the negative slope at the rightmost endpoint. This isn't necessarily applicable to every data set, but it will work on ours. The algebra is fairly simple. Throwing that seventh equation into the mix gives me this. And those 7 equations can be represented in matrix form, as seen here. Our goal is to solve for the d vector. That is represented symbolically here. Again, let it be mentioned that taking the inverse of a matrix directly is not the preferred method of solving a system of linear equations. There are better ways of doing that, and perhaps someday we can elaborate more on such methods. In this slide, I've just plugged in the values for y from our original data table on Runge's function. Then I simplified a bit. This is the solution for the d vector, found by solving the system of equations. I have omitted the details of that and simply posted the result here. Now that the d's are known quantities, I can solve for the coefficients a, b, and c for each segment. The results are summarized here. So what's the deal? With piecewise quadratic spline interpolation, we can impose continuity of position and continuity of slope. You'd think that more constraints would give us a better approximation. Well, the missing ingredient could be related to curvature. Curvature is a way to measure how much a function or a curve bends. So the red squiggle on top has more curvature than the blue squiggle below it. A line, seen in green, has 0 curvature. Curvature is related to the second derivative. For a quadratic, that is equal to a constant, so we have no control over that once a, b, and c have been found. The curvature is not continuous and changes abruptly between segments. In a cubic, however, curvature is a function of t. That gives us some wiggle room to ease the transition in curvature from one segment to another. In the process, it seems that doing so reduces oscillation as well. A note of interest before we conclude. The second derivative of a linear segment is equal to a constant as well. But that constant is 0, so it is the same for each segment. So in that sense, it does better than a quadratic. The downfall of linear segments, however, is that they lack continuity of slope. So we have kinks at the joint between segments. In conclusion, I can say that piecewise cubic interpolation is our best bet of the 3. It gives us continuity of position, slope, and curvature. That results in a smooth curve and minimal oscillation between data points. If you missed the earlier lessons on cubic splines, go back and check them out for more information. Let me know if you have any thoughts on this stuff in the comment section below. I greatly appreciate your support. See you next time.